This video we're going to consider some more about hypergeometric distributions and see what happens if we change some of the defining parameters, how that affects the distribution. So remember that the hypergeometric distribution depends on knowing these three parameters: little n, which represents the known sample size; capital N, which represents the initial total number of items in the whole population, in other words, the population size; capital M, the initial number of successes in the population; and X, which is our random variable, the number of successes in the sample. So the first three are defining parameters, then the X is our random variable. Remember, this is done without replacement on our selection, so P equals M over capital N is the proportion of successes in the population, and that's the probability of a success on the first trial. But the probability of success varies, is dependent then for each successive item depending on what we got before that. Q is 1 minus P, probability of a failure on the first trial. Turns out that the mean is N times P. The standard deviation is given by this formula. Without this factor, it would be the same as the binomial. The mu equals NP is the same as the binomial. But this extra factor is there. Sometimes it's called the finite population correction factor. And of course, the PDF is given by this formula, as we have seen. So we have these three parameters, N, M, and then the other N. And what happens if we leave two of those fixed and change the third one? So for example, here, I'm leaving the population size fixed, in this case at 100. The number of successes in the population is fixed at 30, so that makes P fixed at 0.3. The proportion of successes in the population is 30% or 0.3. But what I'm doing is I'm letting N go up, 4, 8, 12, and so forth, up to 52. And we see the mean, standard deviation, and skewness computed here. And we see a few graphs of some of these. And we can see a few things happen. Well, first, most obvious thing is, if you increase the sample size, you increase the number of bars in the histogram. That's going to be true for a binomial or a hypergeometric, because you have one bar for every value of x, and you have x values going from 0 up to n. So you always have n plus 1 bars. So, for example, when n is 4 here, we only see 5 bars, 1 for x equals 0, 1, 2, 3, 4. When n is 8, we see bars for 0, 1, 2, 3, 4, 5, 6. 7 and 8 are also here, even though they're kind of small, and so forth. And so we see more and more bars as we go along. But we also see, since the mean is N times P, leaving P fixed, increasing N is going to increase the mean. And the standard deviation, if you look, is also increasing. But the skewness is actually going down, so it's getting closer to being symmetric, kind of as we go along here. All right, what if we vary the number of successes in the population, but leave the size of the population and the sample size fixed? So the size of the population here is 100 in all these examples. The size of the sample is 10 in every example, as you see here on the graph and in the table. And we're changing the size of successes going from 0 up to 100 by tens. Now, of course, 0 and 100 are kind of special cases, because if there's 0 successes, the probability is 0. Everything is always a failure with 100% probability. So no skewness, no standard deviation. A mean is 0. Mean is 0. And if it's 100, if they're all successes, then the probability of a success is 1, and the mean is all of them, 10, with no standard deviation and no skewness. Those are kind of special cases. But then the others are going up here, and we see that the mean is increasing as we increasing the number of successes in the population increases without increasing the number in the population totally. That increases the probability of success P, and you can see it going up by tenths here, which of course increases the mean as well. and we see this. Now there are a couple things else that you may notice. The standard deviation actually goes up and back down, and its highest standard deviation when the p is 0.5, but you have zero skewness there, so it's more spread out but perfectly symmetric in that case. So like the binomial, when your probability is less than a half for the p, it's going to be more concentrated on the right and more concentrated on the left, skewed to the right, and vice versa for probability greater than a half. And when the probability was 1/2 right here, this one is perfectly symmetric. Okay, what if we leave the m alone, leave the n alone, but vary the leave the sample size alone, leave the number of successes in the population alone, but increase the population size? Well, that's going to make the p-value go down. Okay, anytime you fix the sample size, you have a fixed number of bars. And by taking the leaving the n fixed and decreasing p, then the mean is going to be going down, and we can see that. And it turns out the skewness actually, goes up and then back down. I mean the standard deviation, and the skewness looks like it's basically going up, becoming more and more skewed to the right there. Now this one is probably the most interesting one here. What if we leave the proportion of successes in the population the same, but increase the value of n? Well, if we leave the proportions to be 40% or 0.4, when we increase n, the population size, we're increasing the number of successes in the population proportionally, so that it always stays 40% or 0.4 times the population size. So both of the n and m are going up the same, but they're doing it in such a way that the proportion stays the same, but we're going to keep the sample size the same. We'll notice that the mean doesn't change, but the standard deviation is actually increasing, and the skewness is actually increasing. But look what it's approaching. If you look at a binomial distribution, and here I've gone up to let me back up here. Look at n. N's going up 10, 20, 30, 40, 50, 60, 70, 80, and then I jumped up to 100, 500, 1,000, 10,000. If you look at 10,000 here, this is what we get for a hypergeometric. And look at a binomial with the same n, the same p, turns out to have the same mean, and look here. The standard deviation is almost the same, and the skewness is almost the same as well. So it turns out that if you take this situation and you let the sample size the population size get larger and larger and larger and larger and larger, it approaches a hypergeometric approaches a binomial distribution with the same n and p. And you kind of see that at the pictures here. So here we have a binomial with n is 10 and p is 0.4 in all these cases. So the graph on the left is always the same binomial. Okay, some of these have different scales for the vertical axis, which is why even though these are exactly the same binomial on the left, they may look a little different. It's because the scales are a little bit different here. But here is the hypergeometric, and really doesn't look very much like it at all when the population is only 20. Yeah, not really much like it. And you're choosing 10 of them, so you're choosing half of the population. So it's quite a bit different than the binomial distribution. But over here, n is 50. It's a little bit bigger, a little bit closer, but still, a significant difference. For example, over here with 50, this is the standard deviation was 1.4 here. Down here it's about 1.5 something. More skewed on the binomial and so forth. When you go down here to hypergeometric with 100, that's this line right here, the table. Now these things are starting to look pretty close to the same. Well, looking visually, it's kind of hard to tell those apart. And by the time we get to 1,000, these two distributions look almost identical, at least to the eye, and you can see that their parameters, the mean, standard deviation, skewness, seem to be all the same or very close. Now this should make sense to you because a hypergeometric distribution is, and the difference in a hypergeometric distribution and binomial, in both cases we're drawing from a finite sample from some population, and in the binomial we're doing it without or with replacement, so that the probability of success each time is the same. In a hypergeometric, we're not putting it back in, so the probability of success is different each time. However, if it's a big population, drawing it out doesn't change that probability very much. Drawing one out is going to have very little effect on the probability of success the next time. So it's almost like a binomial if that population size is really large, and that's basically what we just saw in that last slide. So a hypergeometric distribution approaches a binomial distribution with the same value of p and n as the population size grows. If the population size is sufficiently large, a hypergeometric distribution can be approximated very well by a binomial distribution, and of course the bigger the population size, the better that approximation is. So one way we can think of a binomial distribution is basically like a hypergeometric distribution with an infinite population size. Now, since we have a calculator function or program to compute hypergeometric probabilities, what we will do in my course is we will use a hypergeometric distribution when drawing from a finite population without replacement, regardless of the size of the population, if it is known, because that's the accurate way to do it. Even though it may not make any difference between that and a binomial if the population size is pretty big. But if the population size is unknown, but we expect it to be large, and that's a common situation, then we will instead use a binomial distribution to approximate probabilities which are actually technically hypergeometric, but we'll use a binomial distribution to approximate it, and we know those approximations will be pretty good if that population size is pretty big. Now here are a few demonstrations from the Mathematica CDF demonstrations project that I want to look at. So let's look at this one here. In this one right here, we have a hypergeometric distribution, and with sliders I'm able to change the sample size by leaving this fixed. So the number of marked balls, K, the total number of balls is N. So this is the letters I've been using. This is capital N, the population size. This slider is what I've been calling M, and this is the sample size, lowercase n. They're using the same letter for that. So we can take this and see what happens. So if we change capital N, we can see that moving around there, and you can see the mean is represented by this red dot. It's computing the mean and the variance for us. And you can kind of get a feel for what's happening. As we move these sliders around, so you can see what's happening as we change the big N. Notice the number of bars is fixed, but we're changing big N. We're lowering as we increase big N, we're lowering the probability, so the mean is going back to the left. Okay, let me fix that somewhere. As we change the number of balls in that are successes in the population, we can see that is, as we increase that, we're moving the mean to the right there. Fix that somewhere. As we change the sample size, we're not changing the mean. Actually, we are changing the mean. That scale on the bottom is changing. Okay. Why is the scale on the bottom changing? Well, we're changing the number of bars. So it needs to go from 0 all the way out to 60 here. So that's why they're changing that. So actually, as we increase in, we're changing the mean. It's going to the right. A little harder to visualize that with this particular one. Okay. Let's look at this one here. I think that's the same one we just looked at. Let's look at this one here. Okay, let's look at this one. This is showing a binomial and a hypergeometric together. So this is again, this is the total number of balls that we have, total number of items in the population, and this is the number of successes, and this is the sample size. Let's put it down fairly low at just 15. And you're going to see the difference between doing it with replacement and without. And so you're going to get the two distributions here. And so we're going to see these two overlaid on top of each other. One of these distributions is the binomial, and the other is the hypergeometric. As we get bigger here, if we fix in and increase the sample size where it becomes a larger percentage of the total, we're up to almost, like I said, over half here. Notice that we're quite a bit different here. So if you end up sampling a large proportion of your population, then there's going to be quite a bit of difference between a binomial. Here, only 83.4%. Agreement. But if it's a small n, then like here, n is 15. We're down. Let's say we put down around 10%. Okay, there at 10%, 97.4% the same. But as we increase n, we get a better match, n being the population size. So you can kind of see those together and look at that. And then that was the third one here, and the fourth one, let's take a look at that. Now this particular one actually is, Mathematica has a whole bunch of different discrete distributions built in, and some of these we're going to talk about and a couple of them not. We'll talk about Poisson later. We've talked about Bernoulli. So if I select Bernoulli here and move this back and forth, we can see the information about that. This one's geometric, so you can see how we can move that, and see here is the PDF. Over here is the CDF, except they're connecting with vertical lines, which probably basically should be steps there, but you get the basic idea of what's going on there. Discrete uniform, binomial, important one there. And so it looks like if I just move one of these sliders, it activates that one. So here's a binomial, mean variance, skewness. We haven't even talked about kurtosis, but anyway, there's that, and you can see what happens as we move in and change it, or we can change P. The hypergeometric is here, and so here you can now we're in hypergeometric. Here is what this looks like if you change the defining parameters. Okay, and you can actually mark some different things here. It looks like what you can also do is this is a percentile here. So certain ones you can choose. So if you want the 90th percentile, it's going to figure it out here. Or you have certain ones that you can choose from there, 98th percentile and so forth. So there's a few that we've talked about. We've talked about Bernoulli, geometric, binomial, discrete uniform, hypergeometric, and we will talk about Poisson just a little bit. And but then there are a few other ones there that you could look at as well and play around with those as well. So if you look at these different links, then you can get to that site that we were just at and experiment with some of these. Okay, so let's kind of review a binomial versus a hypergeometric again. Little n is the known sample size. Capital N is the initial number of items. Capital M is the initial number of successes. This is in the total population for capital M and capital N. X is the unknown number of successes in both cases. But the difference is binomial is done with replacement, so that the probability of a success, which is capital N over capital M, that's upside down. All right, now that's better. But that is the probability of a success on every trial. Q is 1 minus P. Well, over here, P equals M over N as well. But that's only the probability of success on the first trial. After that, the conditional probability of a success varies. So it's independent each time. So the probability of success over here in binomial is constant for all those conditional probabilities. They're independent. Now, in a binomial distribution, mu is NP. In a hypergeometric, mu is NP. P is capital M over N. In the standard deviation for binomial, it's the square root of NPQ. And the standard deviation in hypergeometric is the square root of NPQ times this other factor right here. The probability that x equals some value little x, that's the PDF of x. It's given as this combination, n choose x times p to the x, q to the n minus x for the binomial. And we have a formula built into that on the TI-84, binom PDF, and you put it in n, p, and x, and essentially works exactly the same way on the TI-Inspire. In contrast, the hypergeometric, probability of the x equals little x is still the PDF of x, but the PDF is given by this formula right here. And we built in a program on the TI-Inspire ourselves. It was not given to us. But it was this program we called, or this function we called HGOPDF, and you pass it NP and X in that order, and it will figure this out. On the TI-84, we used a program, HGOCDF program, but for a PDF, we just make sure the U and the L there that we enter are both the X value for the probability that X equals that X. Now, if you want the probability that X is between some lower and upper limits, that's the way the CDF works on the TI-Inspire, which of course you're summing from some lower value to some upper value, which is these values here, the PDF version, okay, which is just what the binomial CDF does on the TI-Inspire. You give it the NP, the lower and the upper. Now, so it's truly not a CDF. The CDF on the that's built in on the TI-84 truly is a CDF. It always goes from forever left up to this upper value. So if you do binomial CDF of NP upper, you'll get the probability x less than or equal to this upper value. From that, you need to subtract stuff that's below L, which would be the binom CDF of NP L minus 1. And so this will give you the probability between there. Now, on the other one over here, on this one, the hypergeometric, it's still a sum from L to U of the CDF, but this time it's this CDF. Well, we programmed that in on the TI-Inspire with HGO CDF you pass it N, P, L, and U in that order, and it gives you back the right probability. And we use the HGOCDF program that we program in on the TI-84. So let's look at a few examples of hypergeometric versus binomial. And here's one with a population size of 40, and 15 of those are successes for 0.375 for the probability of success in the first trial. Compare that with the binomial with the same probability of success and the same sample size and the same number of successes. If you just look for one success, you can see, of course, the sample proportion is 0.1. It's the same. You can see the means the same, but you see the variance, standard deviation are a bit different. The binomial has a tendency to be a little more variable. And you can see the different probabilities and how they compare. So they're not exactly the same, but not too far off. But a population size of 40, there's some differences here. These may be agreed to really about one significant digit, basically. And there are the two graphs, and you can actually see they're on the same scale. So you definitely see some differences. They definitely have the same number of bars. They have the basic overall shape the same, but definitely some differences there. If we overlay them on top of each other, and you can see the binomial sticking out higher here, but it's shorter behind this one where you can't see it. So a little different if you overlay them. Here we increase the sample size a little bit here. Go the population size to 160, and let's do 10% of that, which is 16 for the binomial. Again, with that probability of success, and that number of sample is 10. And let's look at the number of successes is 3, and now we see the probabilities are a little closer, but still only agreeing to maybe hundredths place here. And the bars look a lot more alike there. If we overlay them, they would look a little bit more alike. Now let's go up to really big sample size, or quite a bit bigger. Let's do 1200, and let's do a probability. Let's do 720 of those are successes, which is 60%. Let's do a sample of size 50 from that. And we can see, again, they're agreeing to maybe 2 decimal places for the most part. But they are looking kind of alike. So if you don't care about them being too far off, if 2 decimal places is good enough for you, then you could use one of these to approximate the other one pretty well. So again, let's compare and contrast hypergeometric and binomial. In hypergeometric sampling, it's done sampling without replacement, and that's realistic. Usually you go out and once you've sampled something, you don't throw it back and give it a possibility to be sampled again. A finite population is realistic. Okay, most things aren't truly infinite in size. But notice that one limitation of it is you must know the sample size, and that's not always, the population size. You'll know the sample size, but you probably won't know the population size in many cases, particularly if it's very big. So that's pretty unrealistic and not practical. Okay, so what's practical in some cases is this. The binomial, the sampling with replacement, that's not really as realistic. But if the population is infinitely big, the binomial, of course, is appropriate, or if it's done with replacement. So if the population size is very large and the sample size is relatively small percentage of the population size, then the binomial is a good approximation of the hypergeometric distribution. And notice that we have the advantage that we don't need to know the population size here. So the binomial distribution is often used even when the situation is actually technically hypergeometric if the population size is very large, because we do not need to know the population size. So for example, if you were doing something about the number of voters, maybe you just want to know the percentage of voters that were in favor of a certain candidate, you'd be looking at the total number of voters. Well, if you're looking at a country like, say, the whole size of the United States, that's a lot of folks. And we don't know exactly how many are going to vote anyway. And we can't, it's hard to count exactly. So we really don't know how big the population size is. But it turns out it's big enough
that as long, and we're not going to sample anywhere near a large fraction of that population, so a binomial is going to be great for working in a situation like that. Even though technically it's still hypergeometric, but practically a binomial is plenty good enough.